Today, we're setting out on kind of a fascinating intellectual detective story. Our goal? To master the absolute art of separating the true, predictable signal from the chaotic, unpredictable noise in time series analysis. If you've ever tried to forecast data over time, you know it can be a total minefield of statistical illusions. But we're going to clear the fog today. Right out of the gate, we're hitting a really provocative paradox. Is white noise actually something we want in our time series? It's a question that completely confuses a ton of junior analysts and honestly, even some veterans when they first start building predictive models. If this has ever tripped you up, trust me, you are not alone. Take a look at this actual post from the Econometrics subreddit. This user just perfectly captures the frustration. They literally said, "I'm so confused. One article said if it has white noise, it means the time series is random. Another video said residuals should be white noise." It's so relatable, right? Because on the surface, those two ideas seem entirely contradictory. So here's our roadmap to solve this little mystery. First, the white noise paradox. Second, finding patterns in time. Third, the random walk trap. Fourth, stationarity and unit roots. And finally, fixing serial correlation. All right, section 1, the white noise paradox. Let's dive right in and define our fundamental building blocks. We have to understand what white noise actually is. Basically, it's a purely stochastic or random process. It's got a mean of 0, a constant variance, and absolutely no autocorrelation. Okay, what does that actually mean in plain English? It means literally every single observation is a complete surprise. Nothing in the past history of the data gives you even a single clue about whether the next value is going to be positive, negative, large, or small. So, let's resolve this paradox once and for all. If your raw underlying data is just white noise, well, that's bad news for forecasting. It means there's no pattern to find. It's totally unpredictable. However, if your model's residuals, the errors left over after you've actually made your predictions, if those are white noise, that's absolutely fantastic. It means your model has successfully squeezed out every single ounce of predictable signal, and the only thing left behind is pure, unadulterated randomness. Moving on to section 2, finding patterns in time. So how exactly do we diagnose data that actually has a real signal hidden inside of it? We look for autocorrelation. This basically measures the linear relationships between lagged values of a time series. We plot this on a correlogram or an ACF plot. Think of it like an X-ray for your data. On the x-axis, you have the time lag, and on the y-axis, the correlation coefficient. What's really cool is how we read this X-ray. Pure white noise that only show a significant spike at lag 0, just because a variable is always perfectly correlated with itself, and nothing else. But if your data has a trend, you're going to see high correlation for small lags that just gradually fades away over time. Once we spot those patterns, we need a tool to model them, right? Enter the ARMA process, or autoregressive moving average. This is our primary framework. It works by breaking the data down into 2 pieces, a predictable part that's based entirely on past values, and an unpredictable innovation, or shock, which is, you guessed it, our underlying white noise. Now, here is the math behind it all. Seriously, don't panic at the algebra. Intuitively, what we're looking at is the infinite moving average representation of an ARMA model. By using these things called lag operators, which are honestly kind of like mathematical time machines, we can continuously substitute past equations right into current ones. It cleanly isolates those predictable components from the unpredictable shocks, showing us exactly how a single white noise shock just reverberates straight into the future. All right, section 3, the random walk trap. Now we meet the real villain of our forecasting story, non-stationarity. Let's compare a simple deterministic trend with a stochastic trend, which is better known as a random walk. A deterministic trend just grows predictably over time. Simple enough. But a random walk? That is dangerous. In a random walk, the current value is simply the past value plus a white noise shock. It just wanders aimlessly. And because it never reverts back to a mean, its variance literally blows up over time, growing straight toward infinity. So why exactly is a random walk so dangerous? Well, because it leads to spurious regressions. If you run a regression between two completely independent random walks, your software might actually tell you there's a highly significant relationship. It's wild. Look at the symptoms of this sick model: an artificially high R-squared, a massive T ratio, but crucially, a very, very low Durbin-Watson statistic. That low Durbin-Watson points to massive serial correlation in the errors. It's a total statistical mirage. You're seeing a relationship that simply does not exist. Which brings us to Section 4, stationarity and unit roots. So, how do we actually defeat this villain? I want to pose this question directly to you. If a random walk is really just yesterday's value plus today's random shock, how do we mathematically stabilize it so we can actually analyze the thing? The answer is surprisingly elegant. It's differencing. This is our first major statistical weapon. You simply take the current value of the series and you subtract the immediate past value. Bam! You're no longer looking at the absolute level of the data. You're looking at the change from period to period. And the beauty of this is that the first difference of a random walk leaves you with just the underlying shock, which is a perfectly stationary white noise process. Problem solved. Finally, Section 5, fixing serial correlation. Now let's tackle the very last roadblock standing between us and a perfect forecasting model. Imagine this. You've differenced your data, your variables are stationary, and your model looks great. But then you check the Durbin-Watson statistic, and it flags that your error terms are serially correlated. Guys, this is an emergency. It means your standard errors are heavily biased, it gives you false confidence in your results, and literally any statistical inference or hypothesis testing you try to do is completely invalid. You absolutely cannot trust your p-values. To restore validity, we need to pull out our ultimate cleanup tool, the Cochrane-Orchid procedure. This is how we essentially manually model the bad behavior of our residuals. Step 1, we regress the basic untransformed model and pull out the residuals. Step 2, we regress those residuals against their own past values to find rho, which is our autoregressive parameter. Step 3, we use rho to transform the original model through a process called quasi-differencing. And then step 4, we just iterate these steps over and over again until the value of rho stabilizes. Now I should quickly mention a slight upgrade. While Cochrane-Orchid is totally brilliant, it does have one flaw. The mathematical transformation forces you to throw away your very first observation in the dataset. A method called Price-Winston uses a slightly more complex weight on that first observation so you can actually retain it. And in small samples, saving that one single data point can make a real difference in the efficiency of your model. By fixing serial correlation, you ensure that the residuals left behind by your model are at long last pure white noise. You've solved the puzzle. But let me leave you with a final provocative thought. We assume white noise has a constant variance, right? But what if you're modeling something like stock market returns, and the variance of that white noise suddenly starts changing, becoming incredibly volatile during a financial crash? How on earth do you forecast the volatility itself? Well, for that, you'll need to learn about Arch and Jarch models, but we'll save that mystery for our next explainer. Thanks for learning with me today.